All right, kids, so this will actually be the fourth video. The first three videos I filmed in the lab and actually showed you how the reaction is going to take place. So this is this lab that deals with crystal violet, and you'll see in the lab it's a dark violet solution. And so basically what happens is that in this reaction, we're going to change the structure of this thing so that you're going to go from it emits a very bright purple violet, and at the end of the reaction, then it turns colorless. So what's going to happen is that as the concentration of your crystal violet decreases, then you also decrease the vibrancy of that color. Now, I've already explained at this point, you all would have watched the videos, so you know exactly what's going on there in terms of how this color plays out. So here's the nuts and bolts of what we've got going. So here's this reaction. So basically the crystal violet reacts with hydroxides to produce CVOH, which is colorless. So based upon this reaction, it should be dependent upon the concentration of the crystal violet and the concentration of the hydroxide ions. So what we're going to do is we're going to do something clever. We basically are going to make the concentration of the hydroxide ions so big that over this short amount of time, that's going to remain constant. Now, technically, it's going to drop a little bit. So the analogy is kind of like going to the ocean and you take out a spoonful of water. Technically, did you decrease the volume of the ocean? Yes. Is it going to make any difference? No. Okay. So this is what's known as a pseudo rate law. Okay, it isn't a true rate law, but because that would get complicated, because then we'd have to keep track of the concentration of the hydroxide and the concentration of the CV. And so what we're going to do is we're just going to assume that that hydroxide ion is going to remain constant. So here's the nuts and bolts of this. So because these hydroxide ions concentration is so much bigger, we're going to assume that it's not going to change. So that's going to be the first key assumption. Now, here's the next thing. This equation is what's known as Beer's law. Now, don't flip out. No, this has nothing to do with beer. Okay, don't get all excited. It's like, oh, it is kind of ironic that we do have like the coronavirus, and this is why we're doing this on film, but this has nothing to do with Beer's law or the beer or anything like that. So on this, and here's what we're going to do, and this is going to be important. So what we're going to measure is the absorbance. Now, at this point, you would have watched the videos, and so you would know what absorbance is. It's how much light is being taken in. Now, what's important is that the molar absorptivity coefficient and the path length in centimeters, those two values, A and B, are going to remain constant because we're going to use the same size of cuvettes, and that molar absorptivity coefficient is going to be the same. So this whole thing just becomes a constant. And then C is going to be the whole key to this. C is going to be the concentration of the solution. Okay, so that's going to be the key thing. So what we're going to do is that there's two main parts to this lab. So the first thing that I did, and this is what you all have to fill in. This is what you all need to fill in. Okay, is figure out how much water and crystal violet solution I had to mix up to prepare these solutions. So obviously on the stock solution, there was no water, and it was all just the stock solution. So let me give you a hint to get to how much water in stock solution here, just like we did on the iodine lab. You're going to use M1V1 equals M2V2. Okay, so you want, in this case, we're going to mix up 10 milliliters of this stuff. So you can have 10 milliliters of a 12.5 molar solution, and you're going to start with 25. And so, surprise, surprise, to make this work out, you're going to have 5 and 5. So what you need to do is you need to go in and you need to fill out all of this. Now, what I did is I've recorded these numbers. Now, I'm going to tell you right now, you're going to have to draw a graph of concentration versus absorbance. When you do this, when you look at this graph, this point is going to be a huge outlier. So when you draw your best fit line, okay, when you draw your best fit line, this is an outlier, and I'm not exactly sure why. I went back and ran this a couple of times, but when you graph this and you draw this line of best fit, don't include this point. All of these are going to be very, very linear over here. This one is going to be a huge outlier, so don't worry about that. Okay. Now, you'll also see this. This makes sense once you get into the lab. You'll see that the 565 nanometers is the one that absorbs the most light. And now, when you get to these, okay, quick refresh about your quantum mechanics. So the speed of light is wavelength times frequency. Okay. Now, I went old school and I used the Greek letter nu, which is wavelength times nu. Okay. And then your energy is Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. That's a 4, okay, times the wavelength. So this is just a constant, okay, Planck's constant. And so basically, here's the speed of light. So you have that number. You got 565 nanometers. That's 10 to the negative 9th. You want to find the frequency that's going to generate this. And then once you get that frequency, you're going to plug that into here to calculate the energy of that photon. So this is just kind of a nice review of your quantum mechanics stuff. Now, on this one, you're going to draw a graph, okay? And you're going to put concentration here. And you can leave that in micromolarity. And then you're going to have absorbance here. And this is going to get this nice linear graph, except for you're going to have an outlier out here on that 25 micromole, okay? So don't worry about that. So now I'm doing this on the assumption that you all are actually going to draw this graph, okay? So I really want you to draw this graph and draw that line of best fit. And then I want to see this slope. I know I'm old-fashioned, but this is showing me this process. I want to see this graph. I want to see what points you picked on this graph to calculate this slope. So this question about Beer's law, okay? You're going to come up here and you're going to go up, well, this A equals ABC, kind of, I don't know, alphabetic, I guess. So what we're going to assume is that this is going to remain a constant. You're going to know this slope. So here's the tricky part. You're going to know the slope of this line at this point. Okay, so you're going to know this number. So you're going to know your slope. Hold on, back up. I did it in the wrong place. You're going to know your slope. Okay, so you're going to have that number. What you're looking for in this situation, because you're also going to know the absorbance. So what's going to happen is that using that slope, then down here, and I got to move forward a little bit. So you're going to come down here and you're going to know the absorbance, because what happened is that I ran this reaction, and again, this will make sense once you watch the videos. You would have watched the videos at this point. So you're going to know the slope of the line, and you're going to try and find the concentration at that point. So knowing the absorption, and you know that A equals ABC, so you're going to know the slope of this line, you're going to know this number, and then you're going to know your absorbance. So knowing those two numbers, that's going to allow you to calculate the concentration. So then, basically, you're going to take these values and you're going to divide it by the slope of the line. Okay? Got that idea? So this is going to be this divided by your slope to get your concentrations. Okay? So hopefully everybody's cool with that idea. Then, once you get your concentrations, then you're going to take the natural log of these, and then you're going to take the inverse of these. And you're going to draw graphs where you're going to have time on the x-axis, natural log here, and inverse of the concentration over here. Now, this data actually worked out pretty well. And not to ruin the surprise, but you'll see this anyway, what you should see is that your natural log graph turns out to be much more linear than this one does. This one actually is kind of linear, but there's a little bit of hiccup at the beginning. And when you're doing these concentrations out here, like take these out to like 3 decimal places, because otherwise if you don't, you won't, on some of those, it's going to be like the same number again and again and again. So when you're doing these concentrations here, when you're taking the inverse, take those out to at least like 3 decimal places. Otherwise, your graph really isn't going to show up. So I'm going to tell you now what's going to require a lot of thought is setting up the scales for your inverse and your natural logs, because these numbers, when you take them, there isn't much difference in these. So there isn't much difference in your natural logs and your inverse functions. So make sure that when you're doing this, that when you set up these scales, that you leave, like you set up like a big gap in these numbers. Otherwise, you won't be able to see the trend. So I'm going to tell you now, the hardest part is going to be graphing those. So once you get those graphs drawn, okay, then you can come in here. Now you can start to answer these questions. So what you should see, and here's the actual like steps in the instructions. Whoa. Okay. Where you go here, and this is the data that I've given you down below. Then this, you're going to generate this. Then you're going to draw the line of best fit. Again, I want to see the calculations here. So then I'm going to give you a hint. This should be first order because it's the natural log is going to be more linear. Then when you get to this, on your absorption concentration graphs, what I'm asking you to do, and this is a lot of what they're going to ask for on the AP test as well, is that let's say that you've got a graph, and when and this is referencing back to that absorption concentration graph. Let's say that you graph everything, but you get a point that's well below the other point. So in other words, when you look at this graph, okay, and you get a line like this, and you get a point that's one outlier point that's way down here, what could have happened? Or on this one, you're going, oh, okay, right? What's going to happen if I get a point that's well above there? So in other words, all the other ones are linear, but what could have happened to generate a point way up here or a point way down here? Now, here's what I don't want you to say. Don't say, oh, human error. Horrible answer, horrible answer. Human error is bad, okay? Not acceptable. You want to look at what could have physically caused those deviations on that point. Okay, so there you go, kids. I'll be talking to you live in about 20 minutes. I'm going to get all the videos uploaded, and I'm going to send out this graph or send out this lab. And here we go, kids. So that's the story.